Way cool.
Hello, in this video we are going to be doing the experiment VER measurement in the noisy channel, which comes from the D2 TIMS manual. Please turn to figure 5 in the manual, which is the block diagram for modeling the transmission system. We start with the baseband transmitter, the noisy channel model, the baseband receiver, and then finally bit error rate instrumentation. For your convenience, I've already wired up the signal according to the block diagram in figure 5. We'll now look at some of the signals and make various adjustments and discuss them as we go. Starting with the sequence generator, which is clocked from the line code encoder output. The line code encoder is clocked at 8 kHz from the master signals, and 2 kHz is output to the sequence generator, which acts as the bit rate for the system, 2 kilobits per second. On screen we can see we have the bit clock, 2 kilobits per second, and as well we are viewing the digital data output from the sequence generator. Removing the probe, we have a look at the output of the line code encoder, which is output from the line code encoder, which if I single shot it, you can see that it is plus or minus 2 volt level shifted signal. We take the line code signal and input it to the adder. The adder makes up the channel. Into this channel we add noise from the noise generator module, and the output of the adder goes to a channel filter, the baseband channel filter, used to restrict the bandwidth of the baseband channel. Then the output of the baseband channel filter at this point is connected to another adder in the macro model in figure 5 to adjust for any DC offsets. However, in this demonstration we won't worry about DC offsets, and we'll simply introduce another inversion of the signal by passing the signal through the buffer amplifiers, which are down on the master signals panel in the fixed modules. Using the buffer amplifiers, we re-invert the signal a second time so that the signal coming out of the channel is not re-inverted, is no longer inverted. Let's look at the output of the adder with our probe. If we eliminate the signal going into the adder, we will be looking purely at noise from the noise generator. If we input the signal back into the adder and eliminate the noise, and then increase the scale of channel 2, we can see that we have the line coded signal at the output. I've selected the levels of the gains at the adder in order to get an appropriate signal to noise level. I've set the noise generator to a mid-level of plus 14 dB. The gain at the adder is set to maximum, so we have the maximum level of noise going into the adder, and we have a minimal amount of signal going into the adder. The reason we need a high level of noise coming into the channel is because the baseband channel filter eliminates so much of the power of the noise that there's very little noise power left. If we put the noise back in, you can see that the signal in the channel is predominantly noise, but having a look at the output of the baseband channel filter, you can see that there's very little noise and it's predominantly signal with distortion and a little bit of noise. If I adjust the amount of noise by turning the noise generator to 0 dB, you can see that the signal is predominantly the signal passing through the channel and affected by the band limiting of the channel. We have several channel filters to choose from. Channel filters 1, 2 and 3 and 4. Channel 1 is no noise at all, which is convenient. I'm using position 3, which is an optimized linear phase filter, well suited. We can see we have a signal which it will now be presented to the decision maker module. The decision maker is the front end of the receiver, and its purpose is to sample the received signal at the correct instance so as to be able to make decisions as to what the level of the signal is at that instant. Because we're triggering our scope on the bit clock, we can easily view the eye pattern at the receiver. I'm just using 2 channels of this 4-channel scope to emulate a 2-channel scope. Changing the time base, we can have a good look at the eye with a little bit of background ambient noise from the noise generator. If I adjust the time base and then single shot this signal in the time domain, we can see the received signal with its band limiting and a little bit of noise. For now, we'll concentrate on viewing the signal as an eye diagram. The decision maker has the very useful feature of being able to vary the decision point across the eye. So the issue is, when we move the decision point across the eye, we want to choose the optimum point, which happens to be in the middle. So how do we know where the decision point is? There's a signal that comes out of this B and C connector. If you connect this signal to your Z modulation on your scope, you'll have a highlighted point on the eye. Another option is to view the signal simply on another channel of the scope if you happen to have multiple channels. In this case, I'll take channel 4 of the scope, have a look at the signal. As you can see, there is channel 4 of the scope is showing a strobe. This strobe can be varied. As I vary to the left, move it to the right, you can see it moving across the eye. Clearly, making decisions at the transition points of the eye will lead to erroneous results, but position the decision point at the center of the eye for optimum results. If you don't happen to have another channel on your scope, another option is to consult the user manual, and you'll find that the output bit clock from the decision maker is such that the decision point is at the negative edge of the output of this bit clock. So you can see this is convenient. Viewing the negative edge of that bit clock will also tell you where the decision point is. So now we position ourselves in the center of the eye. Even if we have large amounts of noise and the eye appears to close up, we know that we're still making our decisions in the optimum position of the eye. So now the next stage is to set up the signal with not too much noise so that we can align the bit error rate instrumentation. We know that we're set up correctly, so we can take away the strobe signal. Have a look at the input to the decision maker. Just channel 2. Looking at the input of the decision maker. This is an amplified version of the signal from the baseband channel filter. We use this amplifier to control the level of the input signal to the decision maker so that it is set to the preferred input level of plus 2 volts peak, which is 4 volts peak to peak according to the user manual. Set this up, we're on 2 volts per division, and we'll set this up to be 2 volts peak, 4 volts peak to peak, so the thresholds are correct. We have the optimum level, we have a decision point in the middle. Now view the output from the decision maker. You can see that it's a cleaned up line coded version of the input. Okay. Now we'll try to use both of our channels on our scope to look at both the bit clock out. We can look at the clean signal out and the input. Turn off the signal. Use single shot. We can see channel 1, make some changes. At the top we have the band limited input, and at the bottom we have the output from the decision maker. You can see they correspond 1, 1, 1, 0, 0, 1, 0, 0, okay. And without any significant noise, the correspondence is there. So we take that line coded signal, put it into the line code decoder, and out of the line code decoder comes the TTL decoded TTL data signal. You can see once again it corresponds to the signal at the input to the receiver of our system. At this point we now have a TTL version of the received signal. Now what we have to do is count the number of errors in that signal. So we'll use the error counting utilities module, which comprises of an exclusive OR function which acts as a comparator. What we do, we take the signal from the decoder and we compare that with a local sequence from a local sequence generator. We have a second sequence generator module, you can see here, second sequence generator, which has the same sequence in it as our original sequence generator. We're going to compare, take measurements of the number of errors in the channel due to the noise. So we connect the sequence generator to the error counting utilities. The second input comes from the digital output of the line decoder, and we also need a clock, acts as a gate. That signal comes from the output clock of the line code decoder. Just taking a step back, look at these clocks. The decision maker makes a decision, and as well as outputting the sampled signal, it outputs an appropriately phased bit clock. This clock is fed to the line code decoder, which also inputs its own phase clock, which is then passed to the error code utilities. So now we're operating with a local aligned clock, which is aligned to the data. So coming from the output of the exclusive OR is a signal which is a series of pulses corresponding to the errors that I've detected. So now we'll take a lead from the output of the error utilities. We'll take this lead and we'll put it into the pulse counter down on the master system. Now we'll just move the camera down, pan down. Now you can see some errors being counted on the pulse counter. I've taken that error signal from there, input it to the pulse counter, not the frequency counter, the pulse counter. And you can see it's counting the number of pulses, counting up rather quickly. Because we haven't synchronized our local sequence yet, we still have a number of errors. We now take the same error pulse stream and on the black lead, we put this error stream into the sequence generator's reset input. It'll cause the local generator to slide, be a sliding window correlator until it matches the received data stream. I'm about to connect to the reset pulse, and there you go. You can see the errors have stopped accumulating. There are no more errors that are not incrementing, which basically means the recovered sequence with no errors is now exactly the same and aligned with the local sequence. So now that it's all lined up, our bit error rate instrumentation system is ready to count errors created by the noise in the channel. Okay, here's the noise generator. We've adjusted our levels at the adder. As I start to increase the noise incrementally from a very minimal level, you'll start to see small amounts of errors accumulating bit by bit. And now, as we get up to 14 dB, errors are starting to accumulate. The more noise in the system, the more errors accumulate until we dial up till we reach a maximum level of noise. You can see a large amount of errors accumulating. Reduce the noise, you see there's no more errors. So a lot of errors in the channel. If we have a look at this on the scope, pan back up to view the scope, you can see the signal with the maximum amount of noise. It's not an eye pattern anymore because we're not synchronized. Take away the noise and you can see the signal with no noise, signal with lots of noise. So using the bit error rate instrumentation, we can actually count the number of errors by using the bottom half of the utilities module. It acts as a gate. It allows you to count the number of errors for a certain number of clock cycles, so that you can take measurements of your error rate as a ratio of 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6 clock periods. So you'll have a well-expressed bit error rate. So now if you have that bit error rate and the signal to noise level, the student is now able to plot the bit error rate curves versus signal to noise in dB for the system. And using this system, the student is able to compare the performance of this real system with the theoretical expectations. And this same technique can be applied to all the other modulation schemes we have in TIMS, BPSK, QPSK, spread spectrum, and all the other line-coded systems. Now, one thing we haven't looked at this point is how do we actually measure a signal to noise levels. That's simple enough. We take this module, it's a wideband true RMS meter, which has an 8-digit true RMS meter and a 3.5-digit display. It's actually quite an very accurate module. Plug it in, take a lead. Let's take a look at the signal at the decision maker, which is up here on screen. Take the lead, input that signal into the true RMS meter. So now you can see a reading. For this particular level of noise we have 1.62 volts RMS of signal plus noise. If we want signal only, we simply pull out the noise lead. As you can see, the signal is signal only. You can see it up on the scope. Okay, note that measurement, 1.46 volts RMS. Remember, this is a wideband true RMS meter, so it's quite accurate. Put the noise back in, pull out the signal, pull it out from the line coder. So now we have noise only. And the measurement is 0.6 volts RMS. That's the noise only. So 1.46 is the signal, noise is 0.6. So just write that down. We've got, for this particular position of the noise generator, we have 1.46 divided by 0.6, approximately 2, gain of 2, which corresponds to 6 dB. So we know that that reference point is 6 dB. So now, using the calibrated knob on the noise generator, we can easily move in calibrated 2 dB steps. So now we have a reference measurement of 6 dB. We can simply move, take the rest of the measurements off the true RMS meter step by step with the noise generator. Makes it very easy for students to take multiple measurements to define the curve of the bit error rate performance curve. So what we have briefly is a procedure for taking bit error rate measurements in a noisy channel at baseband, and if you want to work at band pass, you can add modulation and demodulation for viewing other passband schemes and quadrature schemes.